Hello, today we're going to be picking up where we left off to talk about adiabaticity. So this is going to be looking at the compression and expansion of gases under adiabatic conditions. So this is actually kind of a good follow-up to last time's discussion on Joule-Thomson coefficient, because when looking at Joule-Thomson effect, we had to make use of compression or expansion of an adiabatic system. So let's go ahead and look at these adiabatic transfers a little bit more in detail. So when we're looking at an adiabatic system, what we're really looking at is, especially when we're talking about compression and expansion, can be simplified to treating a piston with insulated walls. So the only way energy can get into or out of the system is through the action of the piston, as no energy can move through our diathermic walls. And so as a result, we can show this with the first law, because any change in energy is going to be related to the change of work and heat. Well, in this case, we aren't transferring any heat, and any work is going to essentially be PV work. So again, our change in internal energy can be expressed as negative PdV, with an emphasis that we're now talking about the external or applied pressure. However, we've also been able to develop another set of equations to describe the internal energy. And we can go ahead and describe our change in internal energy based on our internal pressure and any change in volume, and our heat capacity and any change in temperature. So this, all of this together should be equal to negative PdV. But most of the time, we're going to be working with a relatively ideal gas. And in terms of an ideal gas, then my internal pressure drops to 0. So then my internal energy is equal to CV dt and negative PdV. So we can actually end up generating a rather simple equation which relates the change in temperature with the change in volume of this adiabatic system. And so this is actually kind of fairly nice. And let's go ahead and look at some of the qualitative features of this equation. So if I go ahead and compress the system, I'm going to have a negative change in volume with a positive pressure. So this means that this whole term should be positive, negative, positive, negative. My heat capacity is going to be positive, and that means that my change in temperature is positive. So this actually helps tell us something that we kind of intuitively grasp, which is that in general, if I compress a piston and I don't let the heat escape, then all of that energy is going to build up inside my system as an increase in temperature. Now, this is actually a fairly important feature when you're working with, say, a lot of engines, or even when you're trying to compress gases, that you have to deal with this increased temperature buildup. Now, in order to try and build up a better understanding of this, let's go ahead and take this equation and try and isolate exactly how much my temperature will change for a given change in volume. So to make this process a little easier, we're going to need to simplify my external pressure, because my external pressure can, well, rather be anything. So let's go ahead and use reversible conditions. So under reversible conditions, my external pressure is going to be the same as the pressure of my system. This also ends up representing the minimum applied pressure that I need in order to conduct a given change. So when I'm looking at a reversible system, I'm going to have a minimum pressure, which will thus give me the minimum increase in temperature for a compression. So if I'm compressing a system, I want to figure out what the minimum temperature buildup I'm going to see for sure is going to be. I can use these reversible conditions. And the greater my applied pressure is more than that minimum, then the higher the temperature, or the faster I compress the system, the hotter it gets. So let's go ahead and look at this in a little bit more detail. So since I have a reversible system, my external pressure just becomes pressure, And I've already made the assumption of a ideal gas, so I can substitute pressure for nRT over V. Now we've got a little bit of our variables on both sides. I've got some T's and V's over here. So what we're going to do is move our temperature over to the right, and we're going to go ahead and consolidate all of our coefficients over there as well. And that just leaves me with a negative dV term on the right. Now, as you may have noticed, I've got a whole bunch of derivatives on both sides. So best way to simplify that is going to be to integrate both sides. So our CV over NR is a constant, so it can come out in front. And what we have is a simple integral of dt over t and dv over v. Well, so again, I'm going to try and consolidate my isochoric heat capacity by turning it to a molar isochoric heat capacity divided by the ideal gas constant. And then when I go ahead and integrate my dt over t term, this becomes the natural log of the temperature differences, final over initial, because yay log laws. And we see the same thing over on the right, where it becomes negative of the natural log of the volume differences. So now I'm going to go ahead and make use of log laws a little bit here. And I'm going to go ahead and take my coefficient here on the left and bring it up as a prefactor. Because again, remember, for natural logs, any prefactor of a natural log can be brought up as an exponent of the inner part of the natural log. Similarly, we're going to do this with the negative out in front of the natural log of volume, and that's going to be the same thing as raising this inner term to the -1 power, also known as I flip my initial and final conditions. Now, since we've got a natural log on both sides, we're going to raise both sides to the exponent, which is just another way of saying we're going to cancel out the natural logs. And now what I have is a relationship in between the two ratios of my temperatures and my volumes. And again, what we're going to see is that these are going to be related through the exponent of our isochoric heat capacity divided by R. Now one of the classic ways we might want to reinterpret this equation is to move all of our initial conditions to the left and all of our final conditions to the right. And when you do this, what we find is that it's going to be equal. We're going to have our initial volume times our initial temperature to the power of our isochoric heat capacity divided by R, equaling the same expression for the right. Now, what this actually ends up indicating is that since this expression has to be equal for any point in this system, it's often expressed as our volume times our temperature to our corrected isochoric heat capacity is going to be a constant. And as I said before, we can also try and use this to figure out our relative temperature increase for a volume change. And so we do this by essentially taking the inverse of our raising both sides to the R over heat capacity, putting R over heat capacity over here on our right, and getting rid of it from above our temperature, and then essentially multiplying our initial temperature by both sides. Now, what this actually ends up telling me is essentially what's going to be the relationship in between a change in volume and my change in temperature. So what I wanted to do is start by looking at the C term. So we know that the minimum heat capacity for an ideal gas is going to be 3/2 R, for again, an ideal monatomic gas, which means our C term is always going to be greater than 1, because its lowest value is going to be 3/2. And this means that our exponent here is always going to be essentially less than 1. So we're always going to essentially see some form of dampening from our exponential term. Additionally, if I have a compression, what we're going to see is that my initial volume is going to be greater than my final volume. So let's say I have an initial temperature. So what I'm going to say is if I half my volume, so I start at a volume of 2, I go to 1, we'd expect our temperature to, by ideal gas law, almost double. But in truth, what it's going to do is a little bit less than double because of this dampening exponential term. So something a little bit interesting here happened here, which is essentially due to the fact that when I'm compressing my system, I'm not going to be seeing the simple ideal gas law, temperature and if volume doubles, temperature doubles, because my pressure didn't stay the same. If I've got a reversible system, my pressure is going to essentially be changing all the time. So we're not seeing this simple linear correlation in between volume and temperature that we would expect strictly from the ideal gas law because we aren't under isobaric conditions. So again, in general, any changes in our volume are going to be greater than our temperature changes. Again, because we have this dampening, this exponential factor coming from our heat capacity. And essentially, the more energy I can essentially pack into my gas, say if I have a diatomic gas where I can pack in a little bit more energy per given temperature of 5 halves R, we're going to see an even greater volume change. However, it is worth noting that this does represent a minimum, because if I have an irreversible compression, then I'm going to see a much greater temperature difference because of my greater pressures. One of the other things that we want to go ahead and watch out for is the fact that this is not isobaric conditions. So even though pressure doesn't show up in here, our pressure isn't constant. It is indeed changing. And so one of the things we might actually want to do is examine what our pressure differences are going to be for one of these adiabatic compressions, in addition to what's happening to the temperature inside the system. So in order to do this, we're going to start with our volume term, which is going to be our easiest measurable term, and we're going to change our ratio of temperatures into a ratio of pressures. And we can do this by more or less inserting our ideal gas log in because we're already made the assumption of an ideal gas. So what we're going to have is for the temperature of our final system, this becomes the pressure and volume of our final system divided by nr. Because again, we're assuming a closed system, so n is going to be constant and r is again a constant by definition. So what we're going to then see is that our constants end up canceling out, and what we relate is the ratio of our volumes are going to be related to a corrected ratios of pressures and volumes for our final over initial system. Now we're going to need to play a little bit more around with this because as we've generally seen before, we really hate it when we have volumes on both sides. So we're going to want to try and condense this equation a little bit. So the first thing we can do is try and move our expression here on the left over to the right. So what we're actually going to do is we're going to multiply both sides by PI/VI over PF/VF. And so then they come out over here. And our volume term ends up staying the same. Now, our pressure is sitting off doing its own thing, so we don't have to worry about it. But we'd actually rather like to combine these two volume terms. However, we can't quite do that while they have different exponents. So what we're going to do is we're going to express the exponent on this term as as 1 in terms of the isochoric heat capacity divided by the isochoric heat capacity. Now this might seem a little bit, why would I do that? But with both of these two terms now sharing the same denominator in their exponents, I can go ahead and combine them together, as they can now be combined as the sum of their numerators. So now we have our pressure times our ratio of volumes times now this interesting term of our isochoric heat capacity plus R over the isochoric heat capacity. But it turns out we actually know an expression for the isochoric heat capacity plus R. It turns out this one's actually quite general. For any ideal gas, this is our isobaric heat capacity. Woohoo! So we change the form of our units from isochoric to isobaric as our exponent. Now, because it's really annoying to write CPM over CVM all the time, we're going to essentially abbreviate this as gamma, where gamma is more or less going to be the ratio of our two heat capacities. And it is worth noting that, again, while still assuming an ideal gas, this won't necessarily have a given volume, because our CV value will differ depending upon the nature of the gas, whether it's monatomic, diatomic, linear, nonlinear. So we can have quite a variance of our CV value even for an ideal gas. Now, what we can do is, since we have all of our terms isolated over here, we can go ahead and separate it out in a couple different ways. One classic way is to go ahead and move all of our initial conditions to one side and all of our final conditions to another, where we're again seeing a little bit of a non-traditional relationship in between pressure and volume than we'd expect to from the simple ideal gas. Because if I had a strictly isochoric compression, this gamma term wouldn't be present. But because our temperature is changing, this is going to essentially dampen our pressure change. And this is what we're seeing with this gamma term. And so what we're going to be finding is that because our gamma term will always be greater than 1, we're going to see, in general, a greater pressure increase than we would for a simple isothermal system. Now let's go ahead and work this by some example numbers. Let's say I have an initial pressure of a final pressure of 1, an initial pressure of 1, a initial volume of 2, and a final volume of 1. So essentially, my volume is halving. Now, if I had a simple isothermal system, my final pressure would be 2. But because this gamma term is a little bit greater than 1, this means that my final pressure is going to be a little bit greater than 2. So essentially, because I'm seeing an increase in temperature for compression, I'm also going to be seeing a little bit excess pressure building up in my system because of this higher temperature, giving me a greater pushback. And we can kind of see this by looking at an adiabatic expansion graph. And again, one of the reasons why some of these relationships can be a little bit confusing is we're used to looking at simple two-dimensional relationships, like our isotherm, which is under a constant temperature regime, and I simply see this inverse relationship in between pressure and volume. But when we're cutting across a temperature change for, say, an adiabatic system, now I've essentially done a slight modification of this general inverse relationship. So let's say I start at some initial pressure, volume and high pressure. And I go ahead and let two systems expand to the same final volume. One in an insulated container, and it turns out that when it's in an insulated container, Well, all of that energy for expansion had to come from somewhere. So it came from the temperature. So the temperature dropped. And because the temperature dropped, the pressure had to drop a little bit more too, simply because there was less energy in kinetic motion to push on the walls. Where if you have an isothermal system, I'm essentially pulling heat from the outside to help drive this expansion. And so this idea of where you get your energy from can have some real important consequences in the expansion and compression of real systems. So that brings us to the end of a lot of our simple thermodynamic relationships. Next time, we're going to do a quick review to try and help keep all of our systems straight. Till then, take care.